This presentation is delivered by the Stanford Center for Professional Development.
Okay, good morning and welcome to EE 364A. This is the second lecture, and in case you haven't guessed, I am not Professor Boyd. He is currently on his way back from India, and he'll be here in time for the lecture on Tuesday. So you don't need to worry, it'll be a proper professor from Tuesday onwards. A couple of things before we move on. First of all, the first couple of weeks are going to be relatively dry mathematical material. So there's a bit of ground that we have to cover before we can do the really interesting parts. So some of that starts today. And as part of that, we're going to be going quite fast indeed. So hopefully lots of you have read or scanned part of Chapter 2, because we're hoping to get through most of that, if not all of it, today. So if you do find that I'm going quite fast today, that's hopefully because I am, and you might find that it's helpful to go back and read Chapter 2 once you're done with this lecture. Before we dig right in, another thing is that we have posted Homework 1. It's not due until, I think, the 17th, if I'm right, which is next Thursday. So Homework 1's already out. Office hours for TAs have been posted, and there will probably be more to come. So today we're going to be talking about convex sets. I'll start off by just describing what an affine set is, and then a convex set. We'll go through some examples. Then we'll talk about how you make more complicated convex sets from simpler ones, and talk about a few other topics towards the end. So this should hopefully be review to start off with. We can form from any 2 points. We can parameterize the line going through those 2 points using a parameter such as theta. Now in this example, theta can vary over the whole real line, and it should trace out the whole line. So we've got a point x1 here, we've got a point x2. When theta is 0, we're sitting right at x2, and then when theta is 1, we're sitting at x1, and it traces out the whole line like this. More generally, an affine set can be described as a set where any 2 distinct points and the line through them are all inside the set. So take any 2 points from an affine set, trace the line through them, and that line better be in the same set. One example of an affine set is a solution set of linear equations, which you've all seen by now. There's lots of different ways of writing it. We can write it with a free parameter, we can write it using an equation on the left-hand side here. But at the end of the day, this is one of the ways you can represent any affine set. A convex set, which is going to be of considerable interest to us this quarter, is one where instead of being able to vary theta over the entire real line, we're instead constrained to having theta be between 0 and 1. And it can take on any value between 0 and 1. So if we find 2 points in our set, instead of before where we could have any point on the line through these 2 points, convex, the line segment described with theta here has theta varying over 0, 1. So to start off with, line segment, theta between 0 and 1, and these are the points traced out by theta as we vary it. So a convex set is a set which take any 2 points in the set, so take an x1 and x2 from your convex set, and the line segment between those 2 points had better be in the set. So that means that an affine set is in fact a convex set, because an affine set contains the entire line through x1 and x2. So of course it does contain the line segment between x1 and x2. So our first example of a convex set is the affine set from before. And this is just a formal way of expressing it here. We pick x1 and x2 out of this convex set C. We vary theta between 0 and 1, and the convex combination of points here has to lie in the set C. Now, here are some examples. This set here, obviously, if I pick, say, these 2 points here, every point along this line lies inside the set. Now, this here is a problem, because if I pick these 2 points here, all of these points here do not lie in the convex set. So that clearly violates this, this set membership here, and this cannot be a convex set. Now this one here is a more technical example, And this one looks like it should probably be convex, but for some of the points where the boundary is missing. So if I picked a point here and a point here, this line actually is not inside this set because it's only got a partial boundary around here. Okay. So these are just some very simple examples described just graphically, constrained to just R2. You'll see quite quickly that convexity can make sense in quite bizarre spaces. Following on from convex combinations, we had just 2 points involved in our determination of whether a set was convex. But the thing is that we can actually extend this concept to a convex combination. So if we pick points x1 through xk, just points to start with, we can describe a convex combination of those points as being a set where we weight each of the points x1 through xk, and the weights all have to be non-negative, and they have to add up to 1. Okay, so this is just a definitional thing at this stage. We define a convex combination as something like this. So if we had if we had 3 points like this, we'll see that the set of all convex combinations actually looks something like this. So if you do the math, you'll find out that as you vary, you need probably, let's make these x1, x2, and x3. If you vary theta 1 and theta 2 and theta 3, and you always have them non-negative, and you vary them so that they sum to 1, the set of points that this sum traces out is called the convex hull of this set. Okay, so we can take any set of points or just a set, and we can form the convex hull by finding all of the convex combinations of points within that set. So let's take these black points here. So suppose someone just handed you these black points and they said, what is the convex hull of these points? And at that stage that sounds fairly unlikely, but later on we'll see why you might be interested. So we take these points and we want to know all of the convex combinations. And so this is the smallest convex set that contains all of these points. And it's formed by basically taking the points at the edges of the set. This is very roughly speaking. You take the points at the edges and you add the line segments involved in those points, and you try and make them as straight as possible, of course, and then you fill in the rest of the set. So if you asked, for example, how I got to this point here, you could form it as a convex combination between these 3 points here. Or in fact, this one lies just directly on a line between these two. So for any set, we can find the convex hull of that set. Here's another example, the kidney-shaped figure that we had before. To find the convex hull of this set, we need to just basically fill in this region here, because that's the problematic region before, where if we found 2 points like this, the line segment did not lie entirely within the set. So any questions so far on convex combinations and convex hulls? Yeah?
What's the difference between a linear combination and a convex combination?
Okay, the main difference is on what you can do with theta. Okay, so an affine combination of points is that we had before is if you have basically free variables. So in fact, a linear combination is this would be a linear combination if we didn't have this constriction restraint here. Okay, so this thing makes it a convex combination instead of linear. Any other questions? Yeah.
Take the convex set C, for example, and then we want to find the convex hull of C.
Right.
So the C again.
Yeah, that's exactly right. So if you already have a convex set and you want to know the convex hull, it's simply the convex set itself, because that set is required to contain all convex combinations. Okay. So the use of a convex hull, if you already have a convex set, the convex hull is useless to you. But sets are by no means likely to be convex in some sense. So it's useful when we want to make a convex set. But certainly if you call, say you had some function conv, and you called it on a convex set, it would simply return the set without trouble. Yes, it is. Yeah, a convex hull has to be convex, again, by that definition. Let's have a look at convex cones now. So first of all, let's introduce a conic combination of points. So this is similar, this is again a specialized version of a linear combination of points. So we take 2 points, we can have more than 2 actually, and we have non-negative weights on these points. And that's described as a conic combination of these 2 points, x1 and x2. Here we have a figure where we have a point x1 and a point x2, and this is the set of points theta 1 x1 plus theta 2 x2, where theta 1 and theta 2 are non-negative. And obviously it's a cone, and that's why we chose the name convex cone. And it also has to be convex. And the reason for that is if we look back to our definition of convex, it was actually a special case of these. We added another constraint on top of this. So if we merely wanted to ensure convexity, we'd only have to check that x was in this cone when theta 1 and theta 2 added up to 1. Okay. So any convex cone has to be a convex set. Okay. So now we have a look at hyperplanes and half spaces. Hopefully you've seen these many times before. And so we start off with just a definition. A hyperplane is a set where A transpose X is equal to some constant B, okay? And A is non-zero, because otherwise we could have any point in a whole set. So this is an example hyperplane. We just parameterize it with a point, say, x0, and then we need to know that A transpose x0 is equal to B. And then any other point that also has an inner product with A of B is also lying on this hyperplane. This is a hyperplane in 2 space, which is a line. In 3 space, you can think of it as looking something like this paper here. This would be a hyperplane in 3 space. It need not go through the origin, by the way. And then following on from that, we have a half space. And this is similar to a hyperplane, but we just take the area on one side of that plane. And we can have it either open or closed. This can be a strict inequality or a non-strict inequality. And this is an example here. Same hyperplane, and it's the half space on the left, or below it, I guess, in this case. And likewise, the non-shaded region you could describe as another half space with A transpose X greater than or equal to B. So the direction of this inequality indicates what side it falls on. A few things. Half spaces are not vector spaces. So if you take 2 points from here, it should be closed. If it's a vector space, it would be closed under scalar multiplication. That's not going to be the case for a half space. So a half space is not a vector space, and people often get that confused. So don't fall into that trap. It's not a subspace either. So that's a hyperplane and a half space. They are both convex. A hyperplane is also affine, which ensures that it's convex, but a half space is merely convex and it's not affine. Yeah. Okay, so it's not affine because we would have to be able to, let's just pop back to the definition. It has to contain the line through any 2 points. So let's pick these 2 points here, and then draw a line between them, and quite quickly we see it's not in the set. Yeah?
Is there a relationship between displacement from the origin and the A and B that are written on there?
Yep, there is. And it's basically, if you find the point that's nearest the origin, and then I think this is actually part of a homework exercise, but if you found, say, that x1 was the point nearest the origin, then you could use A to find out, well, I'm actually going to leave that to you because I think it is part of the homework. But there is a relationship where, yeah, there is one. There you go. That's the answer. Okay, so those are some very simple convex sets. Okay, some more sets that we're interested in. First of all, a Euclidean ball. At the moment, Euclidean is going to mean that we use the 2 norm of in the ball description. So we parameterize a ball by picking a center point xc and a radius for the ball of lowercase r. And it's the set of any point that is nearer in the Euclidean sense to xc than r. Okay? So here's one way of expressing that. Here's another way of expressing it. This is sort of perhaps a free parameter representation where you have a ball u, and it's just a unit ball. You scale it by r, and then you center it around xc. So, sorry, this is the free parameter. So here, 2 equivalent descriptions of the same thing. We can get more interesting than a Euclidean ball and take an ellipsoid, which is a generalization of the Euclidean ball. And that's points that we take a symmetric positive definite matrix P, and we use this expression here. And you can actually go back and forward between this representation for an ellipsoid and this representation for an ellipsoid. And this is just a sample ellipsoid in R2. Okay. So ellipsoids and Euclidean balls are convex sets. And that's probably something that you'll prove at some point in homework. And one of the ways you could prove it is you could find 2 points in it, and you could show that if those 2 points are in the set, then their convex combinations have to be in the set as well. Again, if you haven't read Chapter 2 and you haven't seen these things before, I'm going to be going quite fast, but let's try and get to the good stuff as fast as possible. More generally, we've seen two norms a lot. We've seen the Euclidean norm, but more generally we can define a norm as being any function that satisfies these things here. So first of all, we need, this is something like definiteness and non-negativity. We need to know that it's, so these are just a bunch of things that you should look at that define a norm. You can verify quite quickly that the Euclidean norm does in fact satisfy these, and there are various other ones as well. So just a little point is that this notation here is suggestive of the absolute symbol, which is a norm in the space R. So you'll note that the norm, if you take the absolute value of a number, it's going to satisfy all of these things in the space R. So in 364A, quite different from 263, if we simply have the norm symbol without any subscript, it does not necessarily mean the 2 norm, and in fact it's usually used to represent a general norm. So we've kind of moved up a level of sophistication, if you like, that no longer is it simply enough to just say this is the Euclidean norm of x, but we want to specifically say we're after the 2 norm. Because you'll find and use often different kinds of norms in this course. So we can define, as we saw previously, similar to this Euclidean ball here, for general norms we can define a norm ball. And this ball doesn't necessarily look like a ball. Okay, so it's a ball in the general sense. And we define them very much the same as we defined a Euclidean ball, but they're going to look quite different. So let's just take an example. We have the 1 norm, which is the sum of absolute values. Can anyone tell me what the norm ball with the 1 norm looks like in R2?
Square.
Okay, it looks like, similar to a square, it's actually a diamond like this, if I recall correctly. So the one that is a square, however, is the infinity norm, and that's the maximum absolute value. And that does indeed look something like this in R2. So these are 2 other norm balls. They don't look much like balls, but that's their name. And you could call this the 1 norm ball and this the infinity norm ball. There are others. We can also define a norm cone by adding another variable here and saying the norm cone is any point xt where the norm of x is less than t. So this is our favourite norm, the Euclidean norm, and it's the norm cone traced out. It's got a couple of names. It's called an ice cream cone for obvious reasons, and it's also called, I think, a Lorentz cone as well. So this is actually a solid figure. It might look like a wireframe, but it's actually filled in, and is any point where x is in R2 here along the bottom, and t is up here. So one of the things we know about norm balls and norm cones is that they're convex. So yet again, we're adding another building block, which will become very useful to us later. Doesn't necessarily mean a whole lot now, but just store away that norm balls, norm cones, some of these other things like half spaces, they're all convex, and that's going to be very useful to us later. Any questions on this stuff? What's that?
The cone is filled.
Yes, the cone is filled. Okay, so, actually before I go on, perhaps I'll just mention that if you want to know what the 1 norm cone and the infinity norm cones look like, you can think of these here as a cross-section when you look down from the top of the cone. So if you looked down on this cone, the level sets of the cone would look something like this. And if you looked down on the level sets of these cones here, the cross sections are going to look like this. And so we could fill this in if my drawing lasts for more than one cross section. And similarly for the infinity norm. So you can think of them as a pyramid, and the one norm is sort of rotated, and the infinity norm is a square pyramid. There's probably some fancy name for that. Okay, so here we have a slightly more interesting set of shapes that are also convex. So a polyhedron is the solution set of finitely many linear inequalities and equalities. Here's one of the ways that we can represent it. We can say a polyhedron is any x such that ax is less than b and cx equals d. And that would be a polyhedron. Now, we note here that there's actually a slightly different symbol for less than here. And the reason for this, and you'll often see this both ways. You'll see just an ordinary straight symbol here, and you'll sometimes see this curvy one. Now the reason is because this here is what we got from R. So if we say 3 is less than or equal to 5, this is what we use. But here we're actually sort of overloading this notation to say that AX, which is a vector, is component-wise less than B. And to make this completely explicit, we're using this slightly different symbol here. Now, during this lecture and other times, I might get a little bit sloppy and the curves might not be quite obvious. But the reason for this is because it's actually not quite the same as the ordinary R ordering, and we'll see a generalization of this quite soon. So note that it's different, and the reason is just to make it very clear that we're doing something different to what we were doing before in R. Okay, so positive semi-definite we'll see in a second, and in fact we'll see it on the next slide, so just wait a second for that. So this is one example of a polyhedron here. This is an intersection of a finite number of half spaces and hyperplanes, and so in this particular case we've got 5 half spaces defined by these normal vectors A1 through A5. And you can think of this here as A1 as the half space defined by A1. So if you find the intersection of these 5, you'll discover that it's this shape here. Now, a polyhedron is convex. And this is something that you need to prove. I'm not going to go through it at the moment, but you should be able to show fairly easily that when you find an intersection of a finite number of half spaces and hyperplanes, you get a convex set, and it's called a polyhedron. Now, an affine set is a special case of a polyhedron, and so is a hyperplane from before. Yeah?
This one only uses the inequality, so could you give a quick example of one that actually uses the equality?
Okay, so here's one. Pretend that this is actually an R3, and we've got 5 inequalities like this, and we've got an equality which constrains us to being in this plane. Okay, so they can be anything like that. Next we have a look at the positive semi-definite cone, and that's what you were asking about before. And we say that a matrix is, you should know about positive semi-definite matrices by now, but we define a couple more sets. First of all, S to the n is the set of symmetric n by n matrices. So let's just have a quick look and see, do we suppose this is a convex set? Any suggestions? Okay, yep, it's a convex set. How would we go about proving it? Okay, let's use the definition. So we'll pick an X, which is a symmetric matrix. We'll pick a Y, which is also a symmetric matrix. Now, our requirement for something to be convex, if this is a convex set, then if we take a theta which is greater than or equal to 0, and also less than or equal to 1, and we take theta x plus 1 minus theta y, this set here is symmetric, is convex if each of these things here is also in the set. And is that true for a symmetric matrix? If you take a sum of symmetric matrices, is it still symmetric? Yes, it is. So that means that this is a convex set. Yeah.
Is it in fact affine?
It is in fact affine, yes. And again, yep, you're quite right. The reason for that is because there's no we never used the fact that theta was between 0 and 1. So actually theta could be anything, and we would still have a convex set. It's also linear. So it's all of these things. Okay, so let's look at a more interesting set then. We'll define and use this notation extensively that S sub plus sup n is the set of positive semi-definite n by n matrices. And we'll assume, and especially when we say S, we'll assume that they're symmetric. Okay, so this is a set like this, and just if you've forgotten what positive semi-definite means, it means that when we take a quadratic form such as z transpose xz, it's greater than or equal to 0 for all z. So here's the claim that S plus to the n is a convex cone. Okay, so looking back to convex cones, that means that if we take a non-negative combination of two of these items from the set, it also needs to be in the set. Okay, so you should be able to see quite easily that if we had x that was positive semi-definite and y that was positive semi-definite, if we take a conic combination, theta 1 x plus theta 2 y, this 2 is going to be positive semi-definite. Can someone tell me how I can make that really explicit quite quickly? Yeah?
You can have a z transpose on the left and a z on the right, and use the distributive property to just...
Exactly. So I'll do it like this. I'll say z transpose theta 1x plus theta 2y z, like this. And then I'll expand it out, and I'll get theta 1 z transpose xz plus theta 2 z transpose yz. Okay? And we know that this is positive or non-negative because x is positive semi-definite. We know the same about this. We know that theta 1, theta 2 are both non-negative, and so the whole lot must be non-negative. So we've just shown that if we take a conic combination of two positive semi-definite matrices, the result is positive semi-definite. This means that S plus to the n is a convex cone, and furthermore, it's also convex, as you'd guess when it says convex cone. Okay, we can do a similar thing for positive definite matrices, and here we just add an extra plus to indicate that it's strictly positive definite and not just positive semi-definite. Here's an example of what the cone looks like in, I guess, R2. So this is 2, well, it's not R2, it's S2 plus plus. So this is a cone of positive semi-definite matrices. Yeah.
How did you generate something like that?
Okay, so you generate something like this. Exactly how you do it in MATLAB, I'm not sure, but if you want just intuitively, you could pick a point in the space. Okay, so say we pick this point here. You could find out its x, y, and z coordinates, plug it into the matrix, and you see what the minimum eigenvalue is. And if it's greater than or equal to 0, then it's in this cone. If it's less than or equal to 0, if it's less than 0, it's outside the cone. So I guess if you sort of did a grid search in here, you could build up a set of points which are inside the cone. Yeah?
Can you have a positive definite matrix that's not symmetric?
Yes, you can.
Does it still work? You're not depending on it here? Or?
So this particular picture, it does depend on it because we've explicitly said that. Basically, it's bad form to give somebody a non-symmetric matrix. But because this proof here never used the fact that they were symmetric. Okay, so yes, it's true that the matrices don't have to be symmetric, but there's never really any reason why we would care. So there's no harm in taking any matrix said to be positive semi-definite and immediately symmetrizing it without loss of generality. Okay, yeah.
Just a quick comment about that picture. I think maybe it's point that you could take the determinant of that matrix and you get an inequality y squared less than xz, and then you plot y as a function of x and z.
Right. Yep. Absolutely. So we could actually find an explicit form for the determinant of this matrix, and we could. Well, you'd also need the fact. What's that?
You check out the minors and the guarantees of greater or equal.
Yep. Okay. So anyway, we can generate this plot. Feel free to look into how you do it. I'm just going to move on for now because we do have a lot to get through. Yep.
Component-wise,
just to make it very obvious exactly what we're doing.
It should be just a normal largest sign.
what's this? Why do we? Oh, so why did we use this particular sign here rather than an ordinary one? That's your question. So actually, no. It is a specific. We have specifically used this curvy sign, and that is again because we're not using just the ordinary ordering on R. Okay. So this is now a matrix that we're saying is greater than or equal to 0 in some sense, and it's the sense of positive semi-definiteness. So we've again very deliberately chosen to use this different sign to avoid confusion with the pure ordinary symbol like this. Okay, and you will find some people who use that symbol, and that's okay, just as long as everyone's exactly clear which symbol is being used, which inequality. So now we've looked at some sets that are by themselves convex sets, but it's also, we want to know how to make convex sets out of other convex sets. So there are certain operations that when we apply them to a set, they will preserve convexity. And what it means is that you'll be able to build up more interesting sets from these simple ones that we started with. So if we were constrained to ones that we could explicitly write as equations and explicitly prove were convex, we'd have a lot of work to do if we came up with an unusual set. So first of all, let's have a look at some of these things. One of the ways we can see if a given set C is convex is we can just apply the definition. And sometimes that'll be easy, sometimes it won't be easy. Another way we can do it is we can take operations that are known to preserve convexity, we can take these little atoms that we know are convex, and we can put them together and quite quickly make a fairly interesting looking set. So here's one, an intersection. And this is actually any number of intersections, and I think we look at that on the next slide. And then an affine function will preserve convexity. So if we take a set C, put it through a function f which is affine, it's going to preserve convexity. A perspective function and linear fractional. We'll see those in just a few moments. But here's another way. This is the crude and nasty MATLAB approach. Okay, so say I want to know if a set is convex. And say I've got some oracle which tells me whether a given point is in the set or not in the set. Okay? So here's what I can do. I can pick a couple of points, say x1 and x2, completely at random from the space that I'm in at the time. Then I can test my oracle and I can see if x1 and x2 are in the convex set. Okay? Now suppose they are. Now the requirement of convexity is that when I find this convex combination of these 2 points, that point itself has to lie in the convex set. So if somebody gives you some random set and you just want a very first pass as, is this even remotely likely to be convex? Here's what you do. You make a tiny little window in the corner of your screen, you run MATLAB, and you start generating random points from the set. You take a convex combination and you test to see if it's still in the set. Now, as soon as you find some theta, which is between 0 and 1, where theta x1 plus 1 minus theta x2 is not in the set, and x1 and x2 are, you immediately return it and you say, oh, this is just obvious. Of course it's not convex. Like, you can just see that when you're looking at it. And so it's quite easy to do that. Now here's another thing is that, which I won't go into at length, but basically midpoint convexity, where you just take theta equal to 0.5, that's actually enough, except for some technical conditions. So if you want to run a whole bunch of tests, you could just find x1s and x2s and take their average. And you test to see if the average is in the set. If it isn't, you return it and say, oh, no way it's convex. If it is, you don't necessarily know much. Okay? So it's only useful if it's not a convex set. But if you did, say, 100,000 points, you could give a very rough first pass. And note the quotation marks, it's very rough, it's a heuristic method, but nevertheless, it can be a very fast way of finding out whether something's convex.
When do the one-half midpoint method fail?
Okay, it fails in situations where, we actually had one earlier, it's to do with boundary issues. Okay. So I'm not going to talk about these much, and the focus on this class is not really on this sort of technicality, but if we took these points here, actually, in this particular case, it would work. But say that point there was in the set, then these other points wouldn't be. And you can fill out the rest from there. Okay, so let's have a look in more detail at intersections. And here's the claim. the intersection of any number of convex sets is convex. And fortunately, I can just refer you to your homework because I think you have to show this in your homework for a couple of sets. And when I say any number, that means finite, infinite, and uncountably infinite. So this is a very robust way of finding out whether something's convex. So here's an example, and here it's an uncountably infinite set, I think. And we just take this random thing here, and we know that the individual elements are convex. So we have this, and then we put them all together, and we come up with this shape here. Now, I don't want to dwell on this shape. It's covered in lots of detail in the book, and in fact, let me just take a moment and mention the book. So the convex optimization book is available, and these slides are based very much on the book. So everything here is covered in detail in the book. And the book is also correct from a mathematical point of view. So if I'm tossing around boundary issues and there are little technical differences, we're not going to worry about them in lecture nearly so much, but the book is correct. So if you have done analysis and you are concerned about all kinds of things like closure and closedness and all this, well, they're the same, closure and compactness, then you can go to the book and it will be correct. We're not going to worry so much about that now. Okay. So here's a set where we have an infinite intersection and of convex sets, and it is itself convex. Okay, so let's have another look at a way that we can preserve convexity, and let's have a look at affine functions. So suppose we have some function f that takes Rn into Rm, and it's affine, which one way of looking at this is saying that fx is ax plus b, A is a matrix, b is a vector. Okay, this is actually not the most general way of expressing it, but it's pretty good. So the image of a convex set under the affine mapping F is convex. So if you're given some set S, which is just a set at this point, and it's in Rn, say, then we can use the mapping F and all of the points from X that are mapped into Fx, the new set is a convex set. Okay. Now, likewise for the inverse image. And just to make clear what the difference between these is, suppose we have some set S here, and this is a convex set. If we take this under a mapping F to some other set here, this is the set F of S. And this is a convex set if F is an affine mapping. Now, likewise, we can do the same for an inverse mapping. So if we had another set, these are not very interesting looking sets, but it could be any set. We can take this back via F, and if S is a convex set, then after this mapping, it's also a convex set. Okay. So if we have an affine function, we can actually create quite a lot of damage when we have a known convex set. We can make other ones out of it. Any questions on that? Yeah.
Which notion of inverse are you using? Does it have to be one-to-one?
So it's, well, actually, we don't really run into those issues. So this is the definition here. It's simply the set of any point where the function value of that point maps into the set C. Okay, so it's the inverse image of the set. And so the function, well, it is affine. So is it one-to-one? It probably is one-to-one. But it actually, okay, it doesn't have to be. So it doesn't matter. But it's the inverse image, which is a well-defined thing. And it's always convex if the set C is convex. Okay, so some examples of this. We have scaling, simple scaling by, say, 2. We have translation where we move it around, and we have projection. Now, I'll just briefly mention that the converse is not true. We might have a set f of C that's convex when C wasn't convex. But we're more interested in this anyway. So here's some simple examples. Now, projection could be really simple. We might have a set x1, x2 that we're in C. This might be a point in a convex set C. And if this is convex, then the set of x1, given that there's some, so for some x1, for some x2, the set of just the x1s will also be a convex set. That's just a very simple projection. Okay. A more interesting one is what's called a linear matrix inequality, or an LMI. And this is the set, this is actually an affine mapping here. So if we have a set of matrices AI, and they're all symmetric matrices, then the set X, where this weighted sum of symmetric matrices in the positive semi-definite sense is less than B, that is also a convex set. Okay, perhaps I'll just talk about that one for a second. If we take the cone, let's make a function f of x, and we'll make it equal to b minus a of x, where a of x is equal to x1 a1 up to xm am. So this is an affine function, and it needs a little bit of hammering to get it in the same form as we saw above here, but it is an affine function. Now, we already know that the positive semi-definite cone, which is s plus to the n, we already know that this is a convex set. Okay? So if we take the inverse image of this set here with this function f, what we get is that the inverse image is equal to any x in Rm such that b minus ax is a of x is in the positive semi-definite cone. Okay, and this is just a fancy way of saying that b minus a of x is less than or equal to 0 in the positive semi-definite sense, and then that's the same obviously as ax is less than or equal to b. So we've taken a very innocent looking set, s plus of n. We talked about how that was a convex set earlier. We took also a fairly innocent looking affine function, f of x, and immediately we've got this fairly unusual looking LMI, which is actually a set of weighted symmetric matrices. Okay, well, that's what's on the left-hand side here. It's a weighted set of symmetric matrices. And this is a convex set, and that's with just two very simple ingredients. So you can see that we can cause a lot of damage. Anyone had a question on that? No? So this actually comes up a lot in control, and it's a very useful set. Another one here is the hyperbolic cone, and this one is you can get in a similar way. So we already saw that the set ZU, which is a cone, when we restrict ZU to Z. So we saw this set before. This is a norm cone, and we showed that this was a convex set, or you showed later that this is a convex set. Okay, so we know this is convex, and we want to get to something more interesting. And you can see that if we apply the affine function f of x is equal to p1 half x and c transpose x, the inverse image of this mapping is also a convex set. So if you take this cone here and you map it through here, you get a hyperbolic cone. And again, that's something that will be interesting. So you should verify the details, and as always, details in the book if you need them as well. But here's some quite bizarre sets that are definitely not obviously convex, and you can show quite simply how they are convex, if you know how to do it, of course. Departing even more from obvious sets, we've got a perspective function. And this one's a little bit unusual to start with. There's an example we'll have a look at just in a second. But if I have some function p that reduces Rn plus 1 to Rn by taking the last component and dividing, you can think about it as taking some vector like this, and we pick off the last component, we divide each of these elements by that component, and then we throw this away. Okay, so a somewhat unusual operation, but say I had 1, 2, 3, I'd pick the 3, and my new vector would be 1/3, 2/3, and that's a perspective function. Okay, now the images and the inverse images of convex sets under the perspective function are convex, and that also is going to be useful to us later. So remember, we're just building up a box of tricks that we're going to find useful later. So if it's a bit dry, bear with us for the moment. And there's a domain constraint here that this last entry has to be positive. A generalization of the perspective function is when we have a linear fractional function. So if we have some matrix A, a vector C, vectors B and D, then again, under both the image and the inverse image, the image and inverse images of a convex set under this transformation are themselves convex. And there's a domain constraint on positivity of the denominator here as well. So just to see one example of this, just because it's probably quite a mystifying concept if you haven't seen these before, we take just a set C here like this, okay? And here's a linear fractional function which you can think of as similar to a perspective function or a generalized perspective function. Now if we hold this figure kind of on the side, so if I hold it like this and I look at this figure from a different angle, then I'll find that these parts here are closer to my eye. So if I kind of put the eye here, I think it is, and if I look at this, I'll find that these things loom closer in my vision than the other parts of the figure. So this is quite a strange transformation, and C here is obviously not convex. In fact, why is C not convex? Yeah? Why is C not convex? Someone?
The ridges.
Points in the arms of that starfish.
Yep. So I take a couple of points in the arm. The line segment is very much not in C. Okay. So if this was a convex set, though, under this transformation, it would remain convex. And the reason it's not is because you wouldn't be able to see it too well if it wasn't convex.
Why
Yeah.
does the dotted line move?
I'm actually not exactly sure what the dotted line is about. Actually, probably what it is, it's probably, it's probably a line under the same transformation. I suspect that's what it is. Okay. So another thing you can say about functions is if they transform line segments into line segments, it actually is a convex function. So I suspect that's what it is actually. You'd have to check me, but I think this line moves to this line. And because this line segment moves to this line segment, you can also say that it's a convex function. Okay. So there's some slightly weird functions. Have a look at them later and put them away as things that we're going to find really useful to prove that sets are convex, and that we're going to show some useful things later. Let's now have a look at generalized inequalities. So before we saw moving from a simple inequality in R to a component-wise inequality. And it turns out that it's quite useful to consider other kinds of inequalities as well. Let's introduce proper cones first. So a proper cone is a convex cone with another bunch of constraints. Okay. So first of all, the cone has to be closed. And I'll just mention that some of you will have an analysis background where you know exactly what closed means, and you have read many things about closedness. Some of you don't, and that's actually fine for the purposes of this course. So the 5-second introduction to what closed means is if we have a shape and the set includes the border of that shape, or the boundary of that set, then it's a closed set. If it doesn't include the boundary at every point, then it's not a closed set. Now, if you know what closed means, that was probably an insult to you, but that's actually probably enough. Sort of an intuitive idea of what closed means is probably enough for this course. Okay. So that's the first requirement. To make a convex cone into a proper cone, we add closedness, that it contains its boundary. We also say that it's solid, so it actually has non-empty interior. Now again, interior is another concept that some of you will know precisely what it means better than me. Others of you probably haven't heard it before. You can think of interior from an intuitive point of view as the inside of a set. So the set not including its boundary. So tell me about this here. Using just these rules, if I just have this ray here, is that a proper cone? Why not? Okay, so this cone here, believe it or not, it has empty interior, even though it's getting thicker by the second. But if I just have a ray out from the origin, it has no interior, so it's not a proper cone. There's one more requirement, and that is that the cone cannot contain a line. So that means that, say, this set here, this is a cone, and it's also a convex cone, but it's not a proper cone because it contains this line here through the origin. So this is not pointed. So these are the requirements. It has to be convex, closed, solid, and pointed, and that gives us a proper cone. And we'll find that that's pretty useful. If we didn't have these constraints, when we go to generalized inequalities, they'd fall to pieces quite quickly. Yeah?
Include the theta x of the line.
What's that?
Wait, any theta x inside the convex cone.
So you're saying that any convex cone includes a line. So what about this cone here? This is a convex cone, and it does not include a line. It includes a ray out from the origin, but it doesn't include a line through the origin. Okay, so here are some examples of proper cones. And first of all, the one you're most familiar with is the non-negative orthant. So if I have R2, for example, the non-negative orthant is this portion of R2. And that's a proper cone. So it's convex, it's closed because it includes these boundaries. It's solid because there's certainly plenty of stuff in the interior. That's the technical description. It's pointed because it contains no line, and so it's a proper cone. Here's another example, the positive semi-definite cone S plus to the n. And that's probably slightly more tricky to prove, but all of these concepts generalize into this cone here, so they're not a problem. And then here's another one here, the set of non-negative polynomials, another cone, okay? And we're going to find that this is extremely useful and used all the time. This also we're going to use a lot. This one is sort of a more interesting example, but we probably won't see it all that often. But still, it's a proper cone. Okay, so when we make a generalized, yeah.
Why is that a cone, the third drawing?
1, 2, 3, this one here. It's a cone because it contains, so the definition of a cone was, I think it was just that if I have a point x in the cone, theta x for theta positive has to be in the cone. Okay, so I pick any point in here, and I scale it with a linear factor, and it's still in the cone, right? So I pick this point here, I can scale it positively, and it's still in the cone, and that traces out this area. I pick this point here, I scale it positively, I stay in this area. So you can't find me a point which won't scale and remain in the cone. Right, so this is not, actually it is a convex cone. No, it's not a convex cone. Okay, getting furious head shakes from people. So, yep, this isn't convex now. But and so neither is it a proper cone. Yep.
It contains a line.
Right, okay. Okay, so let's have a look now at generalized inequalities. So before we had this symbol with the curvy lines, now we add a k to it. So if we take a proper cone k, we can parameterize a generalized inequality with this proper cone k. So x we describe as being less than y in the k sense, if you like, if y minus x is inside this cone k. And we can extend strict inequalities in a similar way by saying that x is strictly less than y if y minus x lies in the interior of the cone k. So let's have a look at a quick example, the component-wise inequality that we're familiar with. So this says that x is less than y in the component-wise sense if each of the components xi is less than or equal to yi. So let's take a couple of points, this one here and this one here. X, let's call this x and call this y. Now x is described as being less than or equal to y in this proper cone k if y minus x lies in the cone. So let's find y minus x, and it's this thing here. I'm going to run into a problem. And then y minus x is not in x minus y. This is backwards? Okay, well, yes, okay. So y minus x, what's going on here? Okay, it's pointing to y, right, okay. So y minus x is inside here, okay? Yeah, okay, sorry, excuse this. So if I had a vector 3, 3 and a vector 1, 1, subtract them, I get 2, 2, it points to y, and this is inside this proper cone here, okay? So that's a component-wise inequality. And we can say the same about a matrix inequality. We've seen these before, but we never really made it, well, actually, we did make it clear what was going on. X less than y in this PSD cone here means that y minus x is positive semi-definite. So these are so common that we drop the subscript. Not only that, but we often also drop this special symbol and just use an ordinary symbol like this. So for the purposes of clarity, it's a good idea to stick with this. If it's obvious what you're talking about, you can drop the k, and sometimes people will even just use an ordinary symbol. As you'd expect when we're using the same symbol generalized, a lot of the things that we saw before carry over, and the properties are analogous. So we have things like this here, and this property will carry over. However, be careful because not everything does. And one of the things that doesn't carry over is we don't have a linear or a total ordering. And that means that if we find x and y, they may actually be, x may be neither less than y nor greater than y. So here's another way of expressing that. This generalized inequality here is not in general a linear ordering. So yeah, like I just said, we may have neither of these holding. So that you can see that quite easily in our usual case here. If I have a point here and a point here, then this point in the sense of component-wise, it's neither less than this point nor is it more than this point if you look at all of the components. So it's not a total ordering. So we now introduce yet another concept in this lecture, that x in a set S is described as being the minimum element if, with respect to this generalized inequality, if any other point inside the set is actually more than x in this k sense. Okay? So that's one concept, and we'll have a look at a picture in a second. A second concept is a minimal element when we describe it as we describe an element x as being minimal if any other point that is less is actually the same point. Okay, so that's perhaps a little bit bizarre to start with, but let's just have a little look at that. And here's some pictures. So we're going to use the cone k is equal to r plus to the 2, so component-wise inequality in R2. And this point x1 here is the minimum element of S1. Now what that means is if I pick any other point y in S, then I can explicitly say that x1 is less than or equal to y. And that will hold for any point in here. Now let's have a look at this different set here, S2. Now, what we need here is that I pick x2 and S2, and x2 is a minimal element. And that means that if I pick some other point here, I know that if y is less than or equal to k, less than or equal to by k to x2, then it means that y is equal to x2. So here's a point, for example. Make that y. Now, it's not, x2 is not a minimum element because for this y, I cannot write x2 less than in the k sense to y. I can't actually do that because it's not a linear ordering, so that's not allowed. But I can say that any point that is less is actually the same point. And that's because, here's another way of thinking about it. If I take this cone k, this set here is the set x1 plus k. And that's the set of all points that are unambiguously more than x1. So they can always be described in reference to the cone k as being more than x1. So x1 is unambiguously least. Now in this set, if I drew the same figure here, these are all of the points that are unambiguously more than x2. But this point here is not, well actually let's pick this point y here. It's not in this set, so I can't say that x2 is unambiguously less than y. But what I can say is I can form this other set x2 minus k. And this is the set of points that are unambiguously less than x2. Okay, so any point in here, I can say with full authority, this is a point that's less than x2. So that means, because I find that there are no points inside the set S2 that are unambiguously less, I can describe x2 as being a minimal element. Okay, so it's a slightly confusing terminology here, but here's how it goes. A minimum is something that you cannot, under any circumstances, claim that there's a better point. It's definitely better. There's no less point. Okay, a minimal element means, all points are more is what you say for minimum. So it's very confusing, even when you've seen it before. So minimum, all points are more. Okay, minimal, no points are less in this unambiguous sense. Yeah.
Is the only reason we're using that square because K is the non-negative order? If there was some other set, proper cone, would you have to draw the shape of that cone?
Exactly, right. So let's say, great question. So we could have a different cone. We could have this cone here. This is a proper cone, and we could call this K2, okay? And then we could again look at this, and we could say, we could talk about this relative to K2. So quick question, how would you describe x1 relative to the generalized inequality parameterized by the cone K2? How would you describe x1 in terms of S1? Okay, it's minimal. So it's no longer minimum because the set doesn't lie inside this cone. So there are points that are incomparable, if you like. There are points that you could argue were actually no more than this in an unambiguous sense. Okay. Right. So that's going to be useful to us. And let's introduce another concept while we're on a roll. So this one is the separating hyperplane theorem. And it says that if we take two general convex sets, C and D, and if they're disjoint, i.e. they have no intersection and C intersect D is the empty set. Okay. So if C and D are disjoint, then there is some A not 0 and there's a B, so that the half space A transpose X less than or equal to B, that X in C lies in a half space A transpose X less than or equal to B. Okay, so and then the opposite holds for X in D. So here's a couple of sets. Here is a hyperplane between the sets, and if it's an R2, then it's a line. But you can also think about it as looking down a projection of R3. And this says that we can find some hyperplane so that D lies entirely in this half space here, and C, if you like, lies entirely in this half space here. And it's called a separating hyperplane for quite obvious reasons. And this theorem, which I think is proven in the book, says that any two sets like this that are disjoint, there has to be a separating hyperplane. Now, strict separation, i.e. strict separation requires more. So I won't go into the details here, but strict separation would be a hyperplane that actually passes through neither set. So we can use this separating hyperplane theorem and turn it into another one called the supporting hyperplane theorem. So a supporting hyperplane we define as being one where so here's a hyperplane like this, and this is described as being a supporting hyperplane if the only point that it touches is, if it goes through x0 and all of the set is on one side. Okay, and so you can say that if C is a convex set, that at every boundary point of C there will be a supporting hyperplane. Okay. Now let's try and connect these two new ideas together. So we have a separating hyperplane theorem which says if we have two sets and they're disjoint, we can find a hyperplane that separates them, and one which says that if we have a convex set and a boundary point, we can find a supporting hyperplane. Now we can actually use the separating hyperplane theorem to prove this one, just a moment. And so we can actually say we'll form a set x naught, okay, and we'll also form a set interior of C, okay. So we take a convex set C, we'll assume that it's convex by just looking at this part of it, and we'll say that x0 is one set, and it's convex because it's just a single point, and then the interior of C is a convex set if C is convex, okay. So interior of C and x0 do not intersect if x0 is on the boundary, and then we can find a separating hyperplane between x0 and the interior of the set, and that will be a supporting hyperplane. You had a question over there?
Convexity here?
How did I use the convexity? So it's actually used in the proof. So if this is a non-convex set, and if I have a point here, I cannot find a hyperplane, a supporting hyperplane, because any line through here is actually going to cut through the set. So the theorem says that if C is a convex set, then at any boundary point I can find a supporting hyperplane.
Interior of C and x0 don't have any intersection.
Right.
That's the only thing that you
Okay, so the other thing I used is that the interior of C is convex, x0 is convex, and so C and D are disjoint convex sets. If I set C equal, yeah, okay. So that's, I used convexity of these sets and the fact that they're disjoint to show that there is a separating hyperplane, and I used that to show a supporting hyperplane exists. Yeah?
The example you gave before to square the missing boundary points, its interior was convex. So this,
right.
Is that something special about it?
So, no. I don't think so. So the square we saw before as interior was convex, but yeah, nothing special. Yeah, I mean, this holds for any convex sets. So if the set was the interior of C, all of these theorems would hold. It's just a convex set, and nothing special about it. Okay. Yeah.
But that would mean that the square that it's not unique. Supporting hyperplane could be.
Sure. Yeah, and in fact, if we look at this one here, I could have a hyperplane through here, and this also is a separating hyperplane. And here's a convex shape, and this is a supporting hyperplane, so is this. So these are not unique supporting hyperplanes and separating hyperplanes. So here's another one. We're powering through the material here, and again, I encourage you to have another look through Chapter 2. What we can do now is introduce a dual cone. And dual cones, again, are somewhat strange when you first see them, but they're going to be very useful to us later, and you'll be seeing the word dual, duality, and other things like that every week throughout the course. Let's define for any cone K, it doesn't have to be convex, surely doesn't have to be proper, we define the dual cone, K star, as equal to any point Y with inner product greater than or equal to 0 with a point X in the cone K. So let's just have a look at, let's see what that means. If I have a cone that looks something like this, and I'll call this K, and it happens to be proper, but that's fine. K star in this case is any vector Y where Y transpose X for all X and K is non-negative. So that's actually, let's take this line here. I draw out a right angle here, and so that's a right angle like that. And then I take this one here, and I do a similar thing and draw a right angle like this. Okay. Now this set here is actually the dual cone of K. So this one here is K star. And that's the set of, if I take any vector in here, its angle to all elements in this set here is less than or equal to 90 degrees. Okay? So if I look at this vector here, or in fact any vector in this dual cone K star, its angle to all elements of K is less than or equal to 90 degrees. So this is the dual cone. A few examples. If I look at the non-negative orthant from before, so that's this set here, the dual cone of the non-negative orthant is the non-negative orthant itself. So it's described as being self-dual. And you can see that quite easily if I have two non-negative vectors, y and x. Y transpose x has to be less than or equal to 0. And you should be able to go through a proof of that quite easily. In fact, we could just do yi xi. That's what that's equal to. And so if the components are non-negative, so is the product, and so is the sum. And then the positive semi-definite cone, that's also self-dual. So in this particular case, we actually use a slightly different definition of inner product. And again, details in the book. But if you find the set here, it's going to be the set itself. Euclidean norm cone, it's self-dual. But finally, we get to one that's not self-dual, and in fact, most of them aren't. A lot of the useful ones are, but here's one that isn't, and it's the one norm cone. And the dual cone of a one norm cone is actually the infinity norm cone. Okay? And the other thing that we note is that the dual cone of a dual cone is actually the cone, the initial cone that we're after, if it's a proper cone. Okay, so that's with a big if k is proper, and it may also hold if k is simply convex, but you'd have to check me on that. So what we can say now is that the dual cones, here we go actually, the dual cones of proper cones are proper, and hence we can define generalized inequalities. So if you give me some inequality with k, I can define a generalized inequality with k star. We talked about minimum and minimal elements before, and here is one of the ways that these come into play. So if x is, we have some set S, okay? We know nothing about this set, but let's say that x is the minimum element of S. Now that is true with respect to this, this generalized inequality. X is the minimum if and only if for all lambda that are strictly in the positive cone, sorry, the dual cone, if x is the unique minimizer of lambda transpose z over any point in S, over S, then x is the minimum element. So this is just touching on the very first parts of duality, which is going to come in lots in this course. And it's a little mysterious at first, perhaps, but here's a definition, and it's going to be actually quite fascinating what the lambda means exactly. So for now, that's what a minimum element is. And then a minimal element is a slightly different definition, and it says this: if x minimizes lambda transpose z over S, and there is some lambda, if we can find any lambda that's strictly in the dual cone, then x is minimal. So we'll see later how useful this is. And then finally we can say that if x is minimal, there is some lambda such that lambda transpose z has a minimizer x. Okay. So these things, I'm really just starting to run out of time, so I'm just tossing them out there, and we'll see duality in lots more detail. Okay. So last thing today is what we call the optimal production frontier. And you've probably seen this before, especially in 263 we talk about it with a very simple production frontier. And here's what it says. P is a set of possible production methods. Okay, so on this axis we have fuel, and on this axis we have labour. And say we're testing out different production methods in our factory. If a point is in the set P, it says that there is some production method which, say, produces 100 milk bottles, and it takes this amount of labour and this amount of fuel. So if X is in P, it says there is some possible production method that uses that amount of labour and this amount of fuel. And this is a very simple example in R2. And this set we could find through some marketing guy might tell us what products are available. We might do some research, we might do some testing. There's lots of different ways we could find this set. And what we say is that an efficient method is one that is minimal with respect to R plus to the n. Now first of all, what would it mean if we had a minimum element? So let's say we had X in P, and we're using this generalized inequality with r plus to the n. Now if x was a minimum in the set, it would mean that if I had x here, say this was in the set, then the whole of P would lie within this. And that would say that any production method requires more labour, more fuel, or both than x. Okay, so that would be x being minimal. Now, minimum is a slightly different quantity, a slightly different quality. So if I had x1 here, this is a minimum element. And what it means is that there is no method that requires simultaneously less fuel and less labour than x1. So it's efficient. So any vector along here, there is no method that is unambiguously better. There's none that simultaneously require less of both. Now, labour might be more expensive than fuel, so we might actually want to move along the curve and trade off between them, but we don't want to move off this curve. And likewise, this part of the curve is also efficient methods. Now, the problem with x5 is we can produce at x5, but we could produce at x2, and we would use less labour and simultaneously less fuel. So there'd be no point in picking the method x5 if this was all the parameters involved. So x1, x2, x3 are efficient, and x4 and x5 are not. And you can think about these as being minimal with respect to r plus to the n. And there's other ways that we might be interested in a different cone, and there might in fact be a minimum for a different set. But this is just tying at least one of these things into a practical application. So any final questions? So we are done, and Professor Boyd will be back on Tuesday.